Move fast. Trying to move fast. What? Okay. Okay, good news. We've got audio. Yes. This is fantastic. Arden, you want in here too? This is great. Yeah, Arden's in chat. Let me turn down call audio a little. Yeah. Yes. It's some kind of massive truck. Yes. Yeah, it's too hot here as well. I went outside and worked on my car, and I was like, that's all I'm doing today. It's exceeding 80 freedom units. Ooh, that is a favorite of mine. And that's based on various gravimetric forces on edge objects that seemed weird, and do enough simulations, they imply that there's a gravimetric source out there. Trans butthole objects. Ooh. I was thinking the same thing. I see. We're talking about metallic hydrogen and spaghettification. I haven't, but absolutely. Oh my god. I'm a Cancer. Oh my god. Jesus Christ. Jesus Christ. Fixing the audio. No, OBS was broken at first. Yeah, for some reason it didn't recognize any of my outputs. And I'm realizing how this works.
Object that is large enough to have been turned into a largely spherical object by its own gravitational pull, but yet has not accrued enough mass to be able to have properly and sufficiently cleared out its own orbital path of other debris. This is the reason
Right.
why. This is the reason why, even though Mercury is a very small terrestrial world, and only slightly larger than Ceres. Ceres has the classification of dwarf planet, whereas Mercury has the classification of true planet, for the simple fact that Ceres shares its orbit with a large number of smaller objects, known as the asteroid belt. I believe
Well,
Kizza just had to disappear.
oh, did he? No, he's here.
Well, he suddenly made a noise that sounded like he was putting a mic down, then hasn't talked.
Hmm.
Oh, sorry,
Sorry, you
guys.
still around?
I was talking,
Ah,
and I have
hey,
horrible lag too. So,
oh dear.
of the two choices, I will go with neutron stars. Actually, I'm kind of interested in those.
Right. Fair enough. So we have one
As,
vote for Ardent from neutron stars and a vote from 3 of 12 for more discussions of Planet X. What of you, Kizza? What is your opinion on the matter?
as an honorable king, I get the deciding vote, and it's going to be neutron stars. Because Planet
Neutron
X.
stars, my favorite. Unfortunately, 3, you lose.
Well, the only thing I really wanted to say on that was that when I was a wee lad, I wanted to be an astronaut. So my parents got me Secrets of the Universe. Are you familiar with that?
That is a rather popular astronomy book that was specifically written for young children about 20 years ago, if I remember correct.
Yes. I got the binders, and they sent the little pamphlets in the mail that you would put into the binders. The clicking is probably my mouse, just by the way. I'm still trying to get my audio right. I don't remember how this works anymore. I have no idea.
Interestingly enough, the clicking, if it's particularly rhythmic, might be the sound of my clock that you hear in the background.
It's my mouse because it's too loud.
Ah,
I'm gonna have to mess with this later.
Anyway,
Because
as you were saying about the secrets of the universe,
how about this? That should work better.
let me just enable sound.
Yeah, unfortunately, I'm pumping voice meter into it, but it's not sounding the same as it would when I normally stream. It's just too loud.
You know, listening to the stream, I'm not hearing any clicking apart from when you yourself are directly speaking, so I wouldn't consider it to be an issue.
Yeah, well,
Aside from the
using my.
aside from
I'm
the
using.
obligatory background noise, I'm not hearing any audio issues at all.
You're not going to hear it because you're in Discord, but I'm sending my mic
That's
input straight into the stream because otherwise you wouldn't
I'm
hear it.
talking about. I'm talking about a moment ago when I was listening to the stream. Listening to the stream 3, I would say the audio quality is good enough. Don't worry about it. Let's talk about the content.
Okay.
We're here to tism about space, not tech.
Well, in the meantime, I'm just going to mute my sound mixer OBS because it feels the need to output it to me for some reason. You can go ahead and continue talking. I will keep fixing this while you do stuff.
Okie dokie. So, I'm just going to go ahead and list one of my favorite facts about neutrons. Some neutron stars are capable of rotating at quite impressive speeds. Now, normally you might suspect that an object.
There we go. Ooh. And now I'm getting no audio from Discord. Great. Huh. Hey, Ginge, can you tell you? Okay. Okay. Yes, absolutely. What is happening? What the fuck is going on?
sized star, and it just keeps smashing them down, getting tighter and tighter and tighter over the sun's lifetime. Now, towards the end of this prospective star's life cycle, let's say it's a bit bigger than the sun. Let's say instead of doing the whole expand into a red giant and then gradually fade out, it goes through the more exciting death throes of a star. That being the humble supernova. The supernova is a process in which the star that is going through its fuel reserves has begun to fuse. It has run out of hydrogen. It has begun to fuse helium into a heavier element, and that it has taken that heavier element and it started fusing it into something even heavier. And it just keeps on switching fuel source, gradually turning it into more and more dense objects until it begins fusing iron. Once the iron has begun to fuse, once it has run out of lighter elements to turn into iron, what happens is that the star suddenly loses the ability to live. And this has some rather interesting effects. Now imagine all of the gravity of our entire sun. Imagine the sheer gravitational force that it takes to be able to take objects as massive as Jupiter from that gargantuan distance and hold them in place to the point where they are not capable of escaping out into the wider galaxy, despite the fact that they are literally traveling hundreds of thousands of kilometers per minute, if not per second. That's a lot of gravity. And it only gets stronger the closer you get to the middle of the sun, or this prospective star. Now imagine all of that gravity is no longer being pulsed by the constant miniature explosions taking place in the form of nuclear fusion. Suddenly, you have a whole shitload of stuff being crushed down with such a gargantuan amount of force that it doesn't really matter that the fusion reaction of iron into heavier things does not, in fact, produce energy. Because what happens then is known as a rebounding effect. The rebounding effect is known as a supernova. All of that mass smashes into itself with such unbelievable amounts of force that it fuses some of that material back into heavier elements, up to, I believe, gold is the heaviest it can get to. And then the whole star says, fuck it, and it explodes out with galaxies away. Now, when a star explodes in this manner, only the most outer of layers actually gets released. Because remember, that force of gravity is still ludicrously strong. So, only the bits that are already on the outside of the star actually get ejected out into the wider universe. The rest of it all gets bottled down into the sun's former core, which, yes, has stopped fusing there, but is now just simply sitting there. However, all of that mass, only the bits that are already on the outside of the star. Remember what I said earlier about angular momentum? To just a couple of itty-bitty kilometers across. But that angular momentum is being reserved, my friend. It's being preserved. And this has the delightful effect of taking an object that is usually several times the mass of our own sun and set it spinning at several hundred revolutions per second. They spin so quickly that if you were to look at a neutron star that has been formed from a recent supernova explosion, and you were to put a pinprick on its surface and watch it go by, it would turn into a line across the sun's rotational equator. For that pinprick would literally be passing into and out of your vision so many times per second that it would blur together. You would not be able to perceive the speed at which it is going, and it is traveling at such a alarming speed that it is just absurd. I cannot describe. This is an object that is usually around 3 to 5 kilometers across from end to end. You are watching this object spin at a speed that is going faster than anything you have ever borne witness to in your life. That is a neutron star. That is how fast they travel. That is how fast they spin.
That sounds like the ultimate Beyblade, not gonna lie.
They are hilarious. I love them.
Yep. Now, if only you could take something like that, shrink it down to the size of a sugar cube, and be able to contain it.
Do you want to blend people? Because that's how you blend people, Kizza. If you were to
Well,
take an object...
that doesn't necessarily sound like a bad idea.
Well. Now I'm just saying something
No.
like that. Not saying literally that, but some sort of.
You misunderstand.
Yes. Okay.
When I say blend people, you're probably thinking if you touch it, your hand turns into a interstellar velocity object. No, that is not what I'm talking about.
Okay.
But you see, a little known fact about the sun is that it has a magnetic field. Hang on a moment. I'm going to eat a piece of garlic bread.
He loves his garlic bread cold, Ginge.
Yes, I do. Very fresh.
Welcome, Wick, by the way, for joining us.
Now, the sun has a magnetic field. And that magnetic field is absurd. It is strong enough that it can take loops of plasma and it can effectively contain them. You know when you see an image of a star and it kind of looks like there's a big old archway on that star?
Mm-hmm.
What is happening there is that there is a magnetic field that has decided to be a little bit of a rebel. That has decided that instead of following the gargantuan loops that orbit around the entire size of the star, instead, that magnetic field has decided that it's going to take a shortcut. Instead of going from the north pole of the star to the south pole of the star, it's going to come out on a little bit on the star's surface nearby the equator, do a little loop-de-loop, and then go back in again. Those loop-de-loops have a radius that is often approximately the size of small planets. And that's because there's so much magnetic energy being contained within the star that it just kind of leaks out because it just can't contain it all. Now, fun thing about neutron stars is that they also retain their magnetic fields. And following a very similar principle to the conservation of angular momentum, those magnetic fields also become excessively strong. To the extent where if you take a neutron star that has an especially strong magnetic field to the point of it being given the classification of, pardon me, Magnetar, yes, they have a special designation. Magnetars have a magnetic field that is so strong that if you were unfortunate as to exist in the nearby vicinity of one of these things, and I'm talking hundreds of thousands of kilometers away from it, a magnetar's magnetic field is so strong that much in the same way as you would expect a gravitational field of a black hole to gradually tear bits off of you, the Magnetar's magnetic field is so strong that it can basically do the same thing. It'll just rip bits off of you. The concept of electrical conduction? Nah, forget it. Magnetic fields are too strong for that. They just take the entire concept of electrons orbiting around their nucleus, and it just says, "Fuck that! You're mine now. I'm having your electrons. You get to just exist as a cloud now." Through the power of a magnetar has enough magnetic potential to be able to rip an individual piece of matter apart at the molecular level for no other reason than it dared exist within its magnificent presence. Anyway, I'm going to eat more garlic bread now. Someone else can take over talking.
Well, I brought up the Wikipedia page for Magnetars. I thought this would be a helpful bit of information. Let's see.
I like how one of the neutron stars in the picture just literally looks like a two-piece propeller.
Yeah, it does. Because it's a very simple illustration.
Those are the relativistic jets.
Yeah.
Or, if you think about it, that is the BMW logo there, ladies and gentlemen.
Apparently, neutron stars can be both. It can be both Magnetars and pulsars.
Oh, damn, that's BMW's final form then. Neutron stars.
I thought they were just Bavarian degenerates.
No. Bavarians are actually based.
Really? They're not. Yeah, they're apparently not based enough.
Was the final solution.
Wait,
that's Volkswagen.
Just not good enough.
Technically that's Mercedes, but we don't talk about that. We don't talk about that. We don't talk about that.
I was going to say, I think you would find some BMW engines in certain aircraft.
Well, yeah, because that's what they were founded as at the time. But again, the south of Deutschland über alles, is the engineering heart, where all the good boys are. Stuttgart, Ingolstadt, Wolfsburg, and Bavaria.
Now, because you've been warned, this isn't the topic of the stream.
Yes, I agree, but but yeah, I just love the notion that these giant magnetar things will basically just rip you apart purely because of their magnetic field. I thought initially, the way Ginger was going, it would have such a powerful magnetic field, it basically repels anything. So I could have made a reverse Magneto joke, but technically, if you think about it, it is the ultimate form of Magneto.
Well, no magnetic field would just repel anything. It depends on its charge.
Touche. But to answer Racking's question, yeah, just space in general.
Yeah.
Or I should say, space. It's got to engage in my inner Tim Curry. Because as Hollywood agrees, Brits make the best Russians. Even the Russians agree with us on that.
The best Russian stereotypes.
Tim Curry makes all the best villains, though, to be fair.
We Brits, we're just the best at so much when it comes to acting. We're the best Americans. We're also pretty good at Germans. Who else is there?
Not if Matt Smith is the standard.
Villains. I mean, we are the best villains.
I saw him in a movie recently where he had an American accent.
I would argue that Australians make the best Americans.
Listen. Only one person that works with, and he's not technically Australian, although he did spend a bit of his early childhood in Australian, and that is Mel Gibson.
Although, weirdly, Australians make the best South Africans.
To be fair, an Australian made the best on-screen Canadian. Hugh Jackman's Wolverine.
That is very true. People forget Wolverine's technically...
Yeah, then you got Eric Bana.
Touche,
because
yeah,
the real
Banner's
Canadians
good.
can't be themselves anymore on screen.
Oh, well, yeah, but then again, Batman has been played by an Englishman. Oh, technically a Welshman. Technically.
Oh God.
Yeah, Christian Bale. He's technically Welsh.
Well, that's
Well,
fine.
we shouldn't
Since
hold
we're
that
all a
against
bunch of
him.
mutts.
No, I'm just saying it is a technicality because Wales get shit on enough, so we have to give them some something to celebrate. But that's funny. Red Kings just said Rhodesians make the best Indians, and South Africans make the best Rhodesians. I'm sure a certain utensil would take issue with that. Let's see. Just make sure I'm correct on this.
I wish I had
Yeah.
prepared more for
Yes,
this stream.
yes. American Psycho was born in Wales. Yes, Haverfordwest, which is a town in Wales. That's where Christian Bale was born. So yeah. So yeah, American Psycho is technically Welsh.
Okay, well, back to the topic. I've been
Yeah,
really
you just
interested
know.
in edge solar system objects recently, particularly
Yeah.
the heliopause, because the magnetic field that it has is just as interesting. It might not be enough to tear you apart, but it's enough to create some weird effects.
The helium.
Actually, scroll up to the top quick, Farida, on your regarding your stream. Just scroll up to the top of the wiki article quick.
Okay.
You're scrolling down and need you scroll up.
There's lag in the stream.
To the top. Okay, just right to the
I
top. Yeah,
suggest
that
you-
thing there you just highlighted, the heliosphere. Not gonna lie, it looks like that thing is like trying to penetrate through a wall. Not gonna lie. Looks like it's trying to penetrate through something, like a magnetic field of some kind.
Yeah, that's. Oh God, it threw me all the way down here.
I know.
Here we go.
We're on Cube belt. I thought it was all about Orion's belt.
Orion's belt is quite far away.
Well, everything in space is far away. That's why we need light speed.
Yeah, well, this is a little bit more interesting to me.
Or we just need to be
because
really,
it's
really,
realistic.
really long-lived.
Yeah,
Yeah,
or
but
just
let's
really,
be frank
really
here. We would go
long-lived, yes.
crazy by the time that happens.
Well,
Mm.
it's
I
assumed
have good
that
news.
Probably.
Yeah, more
You-
garlic
you
bread.
finished-
Bionetics.
You finished the garlic bread.
Have
that's
more
the
of
plan.
it? Okay, what's the good news?
The good news is that I'm ready to begin ranting again at any moment.
Woo!
Oh boy.
Well,
I want
I
you to
have to go
rant.
in about 15 minutes, so to get you started, what did you think of
And he gets
What do I
cut
think
off.
of
Oumuamua?
Oumuamua? Ooh.
Yeah.
Wait,
Ooh,
what's this about? Sorry? I
Okay,
didn't hear
so
that.
for those of the uninitiated, who is apparently Kizza is among us, Oumuamua is the first known to be confirmed intergalactic object to have entered our humble solar system.
Well,
wait.
Interstellar
okay,
to be
now
technical.
I remember. It was.
I
Oh, yes.
There were some
Interstellar.
concerns about impact with Earth or something.
I'll throw the link into Events 3 there
it
for
came
everybody.
very, very close.
That is one hell of a probe, not gonna lie.
Oumuamua was never at risk of actually having hit the Earth. What it did was it flew into our solar system, attracted by the gargantuan gravitational field of our own sun. Then, as it was coming towards the sun, it accelerated towards us, and then looped around the sun and started leaving again. We were first made aware of Oumuamua as it was already on its way out. Now, that is the basic information on Oumuamua.
Yep.
The more interesting aspect of Oumuamua is the fact that it did a few really weird things as it was making its way through our solar system. Firstly, it accelerated. Oumuamua accelerated as it was passing through our solar system. That's really weird. Like, I'm
Yeah.
talking I'm talking really weird. Rocks
Like-
aren't supposed to go faster than the force of gravity allows them to do so.
Yeah, it implies it got slingshotted or
Well,
something.
technically, the physicists discovered this, I think it was back in 2005, regarding the universe itself, so yeah.
Are you saying that it was accelerated by dark energy?
Possibly, or...
Well, there
Hang on just a moment.
was some theories about outgassing and things like that, but even so, you
Hmm.
wouldn't expect that to be on the acceleration side so much as the deceleration side
Right.
or the tumbling side.
Right, because you assume that there
Well,
is it does tumble in space, right? Despite it being a long tic
Yep.
tac.
That must be one hell of a tumble.
Okay, so I'll explain to you the current working theory as to how Oumuamua began to accelerate. Because bear in mind, we weren't aware of its presence until it was already on its way out of our solar system, aka making its way away from our
The
sun.
aliens on board looked up and went, "Oh shit, the humans have noticed us! Go, go, go!"
Now, that's what some people like to
Prepare to
think.
fast forward.
It's actually far more interesting than that, believe it or not. It's not just aliens. You see, Oumuamua was it was an interstellar object, or I should say, is an interstellar object. Presumably, it still exists. Now, the thing about interstellar objects is that they don't tend to spend very much time around a star.
What the fuck?
And when you're not nearby any stars, it gets really fucking cold. And when it gets really fucking cold, things freeze. A lot of things freeze, including water,
Oh,
in case you haven't noticed.
I see where you're
So,
going with this. It defrosted a
this
bit when it
means-
came within distance of the sun.
Uh-huh. So what they think happened was that Oumuamua had a considerable proportion of its makeup consisting of what is known as frozen volatiles. Frozen volatiles are a grand generic term used to refer to anything that upon exposure to a source of stellar energy, for example, a star, will begin to sublimate. That is, melt by transforming directly from a solid to a gas. Now, the thing you'll notice about solids and gases is that gases tend to do that whole expansion thing to fill the volume that they are of their container. But space is a really big container, so they never really stop expanding. And due to the laws of physics, this annoying little quirk of the universe, when you have an object that is expanding, that means there is acceleration taking place. So, let's say hypothetically, you have a block of ice. You shine a light bulb next to it. It's in a vacuum, it's in the space, it's just hanging there. When you shine a light on that block of ice, what's going to happen is the light is going to hit the ice is going to begin melting, but because it's in a vacuum, that melted ice immediately turns into water vapor. The ice sublimates. It does not exist in a liquid state for any period of time. And so that ice is then sublimating, but only in the direction of the light source. Meaning it is going to begin throwing gas at the light source whilst pushing itself away from that light source.
Yeah, Newtonian physics.
Acceleration. Exactly. Acceleration via Newtonian physics. Effectively, the sun, by shining its light on Oumuamua, caused Oumuamua to accelerate out of the solar system faster than its own parabolic momentum would suggest it should have been capable of. Now, you may be thinking to yourself, well, that just sounds perfectly normal. That just sounds like something getting turned into vapor, emitting a gas, accelerating. Yes, that all makes perfect sense according to the laws of known physics. And
Yeah, and
You're right.
it's also the same process that gives comets their tails.
indeed it is. A fun fact, by the way, when you see about half of the time when you see a comet with its tail extending out in a certain direction, oftentimes it's actually traveling in the same direction that the tail is. because the tail often doesn't actually have any indication as to which direction it's traveling. It usually just means the solar wind is blowing past it and pushing its tail off in that particular direction. Now, the weird thing about Oumuamua is that it went through the process of accelerating out of the solar system, which makes perfect sense because when we saw it, it was already traveling away from us at speed because we saw it on its way out. The thing that was weird about Oumuamua is that it didn't have a tail. Any tail. It was a solid, inert rock for all that we could see, and it wasn't producing any gaseous byproducts, despite the fact that this rock was exposed to the light of the sun.
And
What
accelerated.
this suggests,
Huh.
and accelerated. What this suggests is that it was off-gassing a material that we couldn't detect. We can detect water vapor when that off-gasses because it does so in the form of water. It has the hydrogen atoms as part of its overall makeup, and we're able to detect that via spectroscopy and things of that nature. If it was off-gassing ammonia, very similar thing. Ammonia is a very simple hydrogen-containing atom. It could have been off-gassing maybe nitrogen. Nitrogen would be a good one, but the thing about nitrogen is that it very quickly resolidifies into nitrogen snow. And a fun fact about nitrogen snow, it's pink.
Nitrogen snow is pink. That's interesting.
Indeed. And it's the reason why Pluto is partially pink. It's there's a lot of nitrogen.
Hang on, the girlfriend just came back in long enough to hear that.
Yeah. The surface of Pluto is pink because it is covered in a thin layer of nitrogen snow. But yeah, Oumuamua, from what we could tell, we couldn't. There was nothing coming out of it, and yet it still accelerated out of the solar system, and now it's gone, and we don't know what the fuck all that was about. It's just gone, and now we have to wait for another one to come in and see what happens with that one. It's entirely possible that when objects do not exist within the heliosphere of a given solar system, that the chemical makeup of the outside of our solar system is so bizarre that there are such weird aspects of physics interacting with chemistry that there are new molecules that we do not know of as currently capable of existing that just simply come into being and gather up on rocks. And when they gather up on those rocks, and those rocks enter into a solar system, and those chemicals turn into volatiles, and they begin off-gassing, that we don't know to look for them. So we can't see what they are. There could be very exotic substances attached to the object, such as Oumuamua, that only exist for a short period of time, that are, for all intents and purposes, unstable upon entering our humble little solar system. And that, to me, is very interesting.
Yeah, it's kind of fascinating because we tend to assume, and I mean, I'm not scientifically
What was that?
illiterate by any means, but not particularly. Oh, okay. I was saying that I'm not particularly scientifically illiterate. I'm not exactly particularly highly educated either, but I've always been of the opinion, or I suppose the assumption, that the general rules of physics that apply around us in our solar system, I suppose, would be somewhat universal. But it's possible outside of our sphere of observation that they're very much not.
Well, that's the thing. The laws of physics and chemistry do not change as you exit our solar system. But what does change is the environment in which those laws of physics and chemistry take place.
Yeah, exactly.
So, for example,
not to cut you off, Ginger, but I actually have to drop out here. So thanks for having me on 3. I appreciate it. I will listen to the rest of this when I have a moment later today.
Okay.
You guys have a good day.
Alrighty.
Bye.
Have a nice day, Ardent.
Okay, so yeah, now that the audio is basically fixed at this point, I'm glad to... Yeah, I'm glad to hear this in all its glory. Would you like to move on to like edge solar system objects, other than visitors, stuff like
Sure.
Voyager,
If you
the heliopause,
if you
whatnot?
you wanna talk about the heliopause?
Yeah, because I looked into it once very late and I don't remember much.
Okay.
It
Well,
was
I
pushing my
see here
limits of
on your
understanding.
stream
Yeah.
the heliopause is well. If you take a look at that image that you had up for a second there, and take a close look at all of the various labels, you will notice that there is a go ahead and full screen that top image there that you see on the.
Okay.
You'll notice that when you take a close look at that image, that there is a variety of structures. First of all, there is the big ovular bullet-shaped thing. That is the heliopause, or the heliosphere. Heliopause is specifically the boundary between the heliosphere and what may be considered interstellar space. Now, what is it that you specifically want to know about the heliopause?
Now, I understand that the heliopause and the heliosphere, they get compressed because they're moving through the interstellar medium. What is the source of that is pushing it in that direction? I understand that it is a magnetic field, but is it...
No, it isn't. Okay, so you may be thinking of space as a perfect vacuum.
And it's not.
Space is not a perfect vacuum. Space exists as a cloud. That cloud gains density of particles in certain areas, and it loses density of particles in other areas. For example, there is considerably more atoms per cubic meter within our own solar system as compared to interstellar space. And again, there is considerably more atoms per cubic meter in comparison of interstellar space to intergalactic space. So, if you take the interstellar space that exists within the Milky Way galaxy, and you were to take a randomly selected cube of a randomly selected 1 meter cube of space and analyze all of the material inside it, you would find probably a couple specks of dust, some hydrogen atoms, maybe a bit of helium, but that would be in an entire cubic meter of space. And you'd find just a couple of little bits and pieces in that entire space. That is pretty fucking close to a perfect vacuum. But it isn't. What that means is that there is still stuff that is providing a medium through which all interstellar, I should say, objects have to try and push through, much like how a boat pushes through water, only on an entirely different scale of density. So, what this means is as the sun is existing, it is constantly emitting its own stream of particles in the form of the solar wind. The solar wind isn't some mystical force that you're able to sail on. It is quite literally just a relatively steady stream of particles, usually a mixture of hydrogen and helium, but sometimes it has a little bit of dust mixed in, that is just gradually flowing out of our sun past all of the various objects that exist within our own solar system. Spyro, could you mute yourself for the moment? Thank you. And it just keeps going and going and going, traveling past Jupiter, Saturn, Uranus, so on and so forth, right the way out past the Oort cloud, which is absurdly far out, bear in mind. The Oort cloud is even further than the Kuiper belt, and the Kuiper belt is where Pluto lives. And it eventually it gets to the point where that cloud of material that is being constantly emitted from the sun gets so diffuse, it loses so much of its momentum that the density of that wind ends up being roughly equivalent to the density of interstellar space. At that point, the friction of the extremely low density of our own solar wind ends up basically coming to an equilibrium with the density of interstellar space, meaning there is a fairly definitive point between which you are in the presence of the sun and not in the presence of the sun. You'll notice that the heliosphere there in this diagram extends off the screen. That is because the sun is leaving a permanent trail of material behind which it is always the heliosphere. However, the heliopause is material that the sun hasn't yet, it's space that the sun hasn't yet traversed, or at the very least hasn't traversed on its current go around the galactic core.
So
Which means it hasn't
the
been there in
heliosphere's
millions of
shape
years.
is caused by the fact that it's moving through the Milky Way.
Yes. The heliopause, there isn't anything especially special about the heliopause. It's
just really
literally
the
just the
edge.
point at which, it's literally just the point at which the heliosphere stops being there.
Yeah. Just the stream of plasma. That's just the edge of the stream of plasma.
You're telling me, Ginger, that Disney's Treasure Planet wasn't real? You cannot sail on the sun.
I hate to break it to you, my friend. But
Well,
no,
that's just the most disappointing news I've had all day.
I mean, not without
least
materials and
you
shielding from 1,000 years
you can't
from now.
you can't sail on the sun's galactic. You can't sail on the sun's wind. What you can sail on is the sun's light, which is far more entertaining. Because the thing about using a sail,
You can use a giant photon sail, sure. I mean, there are
the
satellites
thing about
that do that.
accelerating via the use of wind is that your maximum speed is determined by the speed of the wind.
Yes.
And the maximum speed of light is the speed of light, meaning through the use of a solar sail, you can go up to a significant proportion of the speed of light. You just don't expect to have any particularly great degree of acceleration.
Well, I was going to say, you can't really go anywhere near the speed of light because you'd be too far away from it by then. Unfortunately.
If we were in a bizarre scenario in which you were accelerating away from a star that was not in a galaxy, then yes, you would be able to accelerate away from that star for as long as the net amount of light behind your sail is greater than the amount of
gravitational pull of it.
Yeah. Gravitational pull actually wears off a lot faster than the light pressure, as it's known.
Well, yeah, as long as you're propelled at greater than escape velocity, then yes, you will outpace it, but then cease accelerating as the energy input falls below the threshold needed for further acceleration.
Does that mean
Yep,
you could
pretty
get
much.
significant thrust from another star system?
No, because it's extremely slow form of acceleration, like unbelievably slow. Because photon mass isn't very high, otherwise light would hurt.
To give you an idea as to the kind of levels of acceleration that we're talking about here, imagine you have an aircraft carrier,
meters per
and imagine you have a person with a handheld electric fan standing on the back of it and just holding down the button.
Yes, but in
similar levels of acceleration force.
Yeah, it's useless.
Well, you would have to presume no air resistance in that scenario, which would also defeat the purpose of the fan. But yes, I get what you're saying.
So, the reason why it's so special that, as demonstrated here in this diagram, Voyager 1 and Voyager 2 exited the heliosphere.
What diagram, sorry?
What that means, on 3 of 12's YouTube stream here, I'll repost the link.
Oh, yes.
Expertly.
Of course, it's Tim Curry.
Yes, of course. How could you? How could look? Space. Anyway,
Space.
the significant thing about Voyagers 1 and 2 is that they exist outside of the sun's influence. The only interaction that they have with the entirety of the interior of our solar system right now is gravity and light. There are no other objects that we are able to communicate with, to our knowledge, that can make those same claims. The material that Voyagers 1 and 2 interact with, they don't have anything to do with the sun. Every time Voyagers 1 and 2 bump into a piece of dust, that is dust that has never interacted with the sun. Every time they bump into a hydrogen atom, that is a hydrogen atom that has never touched the sun.
No,
that
helium
is what makes it so special. So, 3. What shall I rant about next?
I'd like it if you talked about the structures in our stellar neighborhood. Because there are some structures other than stars that are interesting.
There are. So, how about I tell you all about rogue planets? So, as you know, a planet is an object that orbits a star. Except what I just told you was a lie. For some unbelievably stupid reason, planets are specifically defined by the international community of people who look up that a planet specifically has to orbit our sun. You may be thinking, well, that doesn't make sense. There are planets around other stars. We've directly observed them with the James Webb Space Telescope. No. Those, you see, those are exoplanets. See how I got you there? Planets orbit the sun. Exoplanets orbit not the sun. It is so fucking stupid. I hate it. I really hate it.
Yeah,
Why can't they just say that? Why can't they just finally decide to get away from the ridiculous nature that is the soul-centric nature of astronomical discussion, and finally admit that a planet is a big ball of matter that isn't a star?
We was
Crying
kings and
out
shit.
loud. Yeah. Anyway, that particular pain point aside, I'm going to do the correct thing and call a planet a fucking planet. So, a rogue planet is a designation of a planet that is bereft of a host star. If you were to look at the orbit of any given planet, whether it be orbiting our star or a star that we are light years away from, what that means is if you were to look at its trajectory of orbit, it would make an ellipse of some kind that takes it on a circuit that results in that planet being in roughly the same location on a regular time schedule around that host star every set amount of time. If you were to look at the orbital mechanics of a rogue planet, however, you would notice that it is not bound to any particular star. Instead, it has its own trajectory. It is its own free, independent astronomical object that is operating in much the same way as a star would. It simply floats around doing its own thing. Now, rogue planets are really hard to see. In fact, pretty much every single rogue planet, if you were to look at it directly, you would not be able to make out any kind of surface features, because rogue planets are about as cold as intergalactic space. I say about as cold because they do generate the teeny tiniest little bit of warmth, generated almost exclusively from what is able to leak out of its slowly cooling
Yes.
core.
So they can be detected either by infrared or by microlensing, with microlensing considered to be the more reliable technique.
Yes, and gravitational microlensing is the process in which you observe something through the simple fact that it is able to bend the light of objects that are located behind it. But typically, the only way in which anybody here would be able to observe a rogue planet is just by simply looking for when a star happens to wink out for the barest blink of a split second that it happens to eclipse that given star. It is worth bearing in mind rogue planets are very unlikely to ever travel at the same trajectory as our own sun. For if they did, they would likely be orbiting our sun. Hang on just a
I can't help but think of the Star Trek Enterprise episode about the rogue planet, where it was basically night all the time. And essentially, it's just like an extended night camping trip, where they had to hunt the animals that were nocturnally adapted. Turns out that they could shapeshift into people, or at least, no, they couldn't shapeshift. They could psychically project themselves into people's minds, and then they would appear as their own species, so that as a technique to adapt to being hunted. I thought that was really fascinating, but I really like that Star Trek Enterprise got into more of the how would I describe this?
Right, I'm back. What have I missed?
Oh, not much. I was just mentioning the Star Trek Enterprise episode about a rogue planet.
Ah.
I don't know if you're familiar with
Star
that.
Trek episode, but bear in mind I have not seen this episode of Star Trek. Would the rogue planet happen to, I don't know, be a giant ball of gas?
No. It was.
How about a gargantuan ice block that is about as feature filled as what you'd expect to pull out of your freezer drawer?
Nope, that's not true either.
In that case, that rogue planet was horrifically unrealistic.
Well, supposedly it had some sort of geological. It had tectonic activity that was left over from the fact that it was ejected from an orbit. It had already had life develop on it, but in some recent century it had left its orbit. So it was left in perpetual night, and also had a jungle full of actual fauna, and they had adapted to these changes. There's still heat being generated by tectonic activity, so you could go down to the planet, and you wouldn't need an EV suit or anything. It was just perpetual night.
That is terribly, terribly unrealistic, I'm afraid. Allow me to explain why. So, the most geologically active... Actually, you know what? Let's give a little quiz. 3. And anybody else who happens to be listening to us and responding in form of text chat. Give me your best guess as to which object in our humble solar system is the most geologically active out of all of them.
Well,
Venus?
It's not Venus.
let me guess. Somehow it's Europa? Yeah.
The black tier gets
No.
the black tier. That is a damn good guess, but it is also
No, it's Io,
wrong.
isn't it?
Correct. The correct answer is Io. And do you know why Io is the most geologically active object in the solar system?
Not really.
Yeah, is it gravity?
Oh, is it?
Gravity is a partial answer.
Part of its tidal existence with Jupiter.
Ding, ding, ding. Now, Io is a moon of Jupiter, and Io itself isn't an especially large moon. It's large in the grand scheme of things, but do bear in mind that the definition of a moon is any object that is natural in origin and orbits a planet. That means that if you were to observe a particularly if you could take a baseball sized rock, hook it hard enough around planet Earth, and that would be considered a moon, because yes, the origin of the object must be natural, not the means by which it entered orbit. It's a rather silly definition, far too broad for my liking. But the point is, Io is a relatively small moon orbiting the second largest and second most massive object in the entire solar system, that being Jupiter. Now, normally that wouldn't be too much of an issue, because it would just simply orbit around and it would be perfectly fine. It would be much like the interactions that you see between the Earth our moon, a moon that I will refer to as Luna from here on out. So, the problem is that Luna and Earth share an orbit that is largely circular. That means no matter what part of the orbit the Earth's moon Luna is on, it's always roughly the same distance away from us, give or take a few kilometers. Io, on the other hand, Io's orbit takes it on a rather eccentric orbit, during which its distance varies considerably. And because Io has an orbit that takes it on a rather eccentric orbit, which, bear in mind, is only made more excessive due to the fact that there are considerably more massive and numerous moons orbiting the same general vicinity. For example, Ganymede, who is a moon that is even bigger than Mercury, a true planet. Io ends up getting a highly variable force of gravity applied to it. So, as it gets closer to Jupiter, the amount of gravity pulling on it increases. And this causes Io to be stretched a little bit. And then, when it gets to the further reaches of its orbit, the force of gravity weakens, causing that elastic force that is the gravitational interior of Io to re-squish again, putting it back into a sphere. What this means is that every single aspect of Io, on a fairly regular basis, is being pulled and squished and molded, much like how you would a paperclip if you were particularly bored during one of your maths lessons as a child. Now, anybody who has fiddled around for a sufficient amount of time with a paperclip will know that if you bend it enough times, suddenly it becomes awfully warm.
I can't wait until
warmth. Oh.
Yeah, I can't wait until these sort of moons become much more accessible with, high impulse spacecraft.
Ooh, I mean, yes. I'm looking forward to that as well.
I'm really thinking like Cowboy Bebop vibes. Like, I really like that time period in science fiction where it's not quite, we might have faster than light travel, but it's not accessible to commercially yet. Like maybe late 21st century, early 22nd century, where most people are flying around on these high impulse but no warp drive interstellar ships.
The number one issue with attempting to achieve high impulse ships is attempting to get these ships to carry their own source of fuel. The problem with that is that one of the most efficient forms of thrust is the ion thruster, and for an ion thruster to work at any significant degree and any significant amount of thrust, you need to have a whole shitload of energy to pour into it. And energy is limited, especially in the outer solar system. The outer solar system being largely defined by past Mars. Now, the Black Tur in the chat there, he asked a rather interesting question. That being, is that the moon with a lot of methane? Or at least I assume that's what he's asking. The thing about methane is that it's not Io. You're thinking of a different moon around a different planet. That is the planet Titan, which is the largest moon to to orbit the planet Saturn. Titan, by the way, is incidentally rather interesting, as it is the only celestial object in the solar system to have surface visible liquids. Besides the Earth, of course.
Yes, Io is very much different in which it has the lowest water content per density of any object in the solar system. It's literally the driest object out there.
Yes, and by dry, 3 is referring specifically to its water content. It's not like a desert in dry. It's more like the interior of a volcano levels of dry. All of that water has been ejected by the excessive amounts of heat being generated by its rather turbulent orbit.
Yeah, it also has the highest density of any object. It's very unique.
It is. It's very unique. In fact, it's often believed that several centuries from now, if we were able to get to the point where we are able to sufficiently exploit the materials of all of the solar system, that Io would be a practically never-ending source of mineral wealth by just simply taking whatever pool of inner material happens to have welled up to the surface, skimming it off the top like you would a boiling bowl of soup, and just see what happens to be there. Think of it. Just think for the moment. Icebergs made of diamonds. They could very well exist on Io. At least in smaller quantities.
I mean, it would be our local Forge world.
Indeed.
I mean, life is going to significantly change once we're able to make regular trips back and forth between these interstellar bodies. I mean, interplanetary bodies, I should say. It's going to change everything. It's going to absolutely crash the value of so many materials. And it's going to make massive wealth possible for virtually everyone that's engaged in this economy. I mean, we spoke on this to some degree in the transhumanism stream, and I cannot help but think of planets yet again, because although it focused on asteroid mining, once we really achieve high impulse vessels and we've figured out how to power ion engines, probably with antimatter reactors or something, or small.
I have a solid idea as to how we are going to be able to achieve high impulse travel, assuming it ever actually happens. What that is that we're going to be able to crack this code of having compact nuclear fusion.
Yeah, that's definitely coming soon.
Once we're able to figure out compact nuclear fusion, now bear in mind, I don't say cold fusion. Cold fusion is a load of bullshit. It's a big old crock of shit. Don't believe it. Anybody who tries to say that we've already figured out cold fusion is operating on scientific concepts that don't make sense.
Yeah, because fusion needs a startup reaction.
Fusion requires you to take 2 atoms of presumably hydrogen and smush them together so hard that the forces that are produced by protons repelling each other via positive nuclear force are overcome to the point of the strong nuclear force then taking those newly introduced particles, integrating them together. That is what is required for nuclear fusion. Cold fusion operates on the assumption that the tendency for hydrogen to integrate itself into certain metals and do so at a high degree of density means that by simply exposing hydrogen to certain metallic alloys, you are able to cause those metallic alloys to soak up the hydrogen like it were a sponge, to the point of that hydrogen achieving such high density within the metallic matrix that they begin fusing into helium. That's not how physics works.
Yeah, I don't have much reason to believe that we're going to achieve that anytime soon. But regular, warm hot fusion. I mean, there's facilities that I'm aware of that are currently tweaking their generators to achieve the max possible parameters, and they will come to the best possible set of parameters within the next 15 to 30 years. They're hoping it's 15, that would assume that they get through half of the permutations. I saw it on the.
It's like they
NCT.
always say, nuclear fusion is only 50 years away.
It's not that far away. I genuinely don't believe it's that far away. I assume.
Well, the problem is right now. The problem is right now is that the issue with nuclear fusion is that they keep on having what I would refer to as false starts. Yeah, I'm sure everybody heard that little cake recent. That amazing example of a nuclear fusion startup having produced net positive energy.
Mm-hmm.
Well, that is nowhere near as great an accomplishment as what you mean. You see, when they say net positive energy, what they mean is that they use lasers to take a gargantuan amount of energy, a gargantuan amount of electricity, that I should say, and very inefficiently and lossily convert that into a rather impressive but significantly smaller amount of laser light. And they then fired all of that laser light at a tiny, teensy little pebble of nuclear fusion material that proceeded to get really bloody hot and undergo nuclear fusion for about 1/10 of a second. At which point, that little pebble of nuclear fuel was now nuclear fuel byproducts, which was then really bloody hot, but they couldn't figure out any way to be able to extract the energy from it because it's just a really hot marble. Now, bear in mind, they lost 90% of the energy put into the entire system because 90% of that energy was lost in the conversion of the material from a 90% of the material, 90% of the energy was lost in converting that energy from electricity into laser. And so as a result, even though the amount of energy that touched the nuclear fuel was less than the amount of energy that the nuclear fuel output upon the reaction ceasing, that was net positive. However, they still put about 100 times more energy into the nuclear pellet from the energy grid as what the nuclear fuel pellet actually produced. Meaning, we're still a long way off. And the most important thing about all of that is that this material, this little pebble, how do you get energy out of a really hot marble?
You need some sort of device that converts heat back to energy.
Yep. You know how you do that?
Boiling water?
You boil water. You make a fucking kettle.
Basically the same thing as steam as nuclear and nuclear fission. It's
right.
really just a complicated way of boiling water.
It is. It is a hilariously complicated way of boiling water. Now, the thing is that boiling water is really inefficient because to boil water, you first of all need to take it through the entire process of bringing it from room temperature, which is usually around 15 degrees C at base. You might be able to get a head start by operating a nuclear fusion reactor in an especially hot country, meaning you'd be able to have your starting temperature be all the way up at 40 degrees C. And then you've got to boil that water. And then it gets to the point where the water has started boiling, and then you get to the really difficult part of energy input. So you see, did you know that about 50% of the energy Okay, so in order to get water from 0 degrees Celsius up to 101 degrees Celsius, about half of the energy input is spent taking that water from 0 degrees Celsius liquid to 99.9 degrees Celsius liquid. The other half of that water is spent taking that 1.5 degrees hump over from being a liquid to a gas. Because such a gargantuan amount of energy is lost and used up in the process of actually getting that water to the point of being a gas, that it's just a whole lot of water and a whole lot of energy. And yes, what Max Damien in the chat there says is true. You can indeed change a substance's dimensions and physics without expending energy, or at the very least without adding or taking away any energy from the substance itself. However, to do that, you need to have a change of pressure, and
that's what I was was about to mention. Is that you could take advantage of the fact that pressure changes the temperature at which substances change their phase, and you could possibly make the process a lot easier one by using a substance that boils at a lower temperature.
Well, you see, the problem with attempting to perform nuclear fusion under a vacuum in order to achieve more efficient energy input and conversion is that you've then got to expend energy maintaining the vacuum.
Yeah, that's entirely why you need a process that requires much less energy to simply to form the reaction.
To quote one of the most intelligent men ever to grace a television screen, it's a moot point, because what the cows have anything.
Mm-hmm.
But yes.
Well,
the thing about the nuclear fusion they realized in recent groundbreaking experiment is that in order to be able to take that logic of achieving nuclear fusion, that being take a pellet of nuclear fuel, fire a shitload of lasers at it, get it to the point of it has begun fusing its interior nuclear material, and then extract energy from that material, you would need to do several things. First of all, you would need to achieve a laser that is able to convert electrical potential energy into laser light in such a highly efficient manner that it is practically lossless.
Yeah.
We can't do that. That is not currently possible by known physics. We're not even close to getting there. Currently, the most efficient lasers are approximately, say, like 70% lossy.
Yeah, the only process
really
that's
bad.
Even theoretically 99% is extracting radiation from a singularity. And how we're going to contain a singularity, nobody fucking knows.
Yeah. It's not likely to happen anytime soon, boys. But what they can do is we can take that laser, hypothetically, we can crank up that power efficiency to the point where every watt of electricity that you put in produces 1 watt of laser light. Let's say we have cracked the code and we've managed to get the perfectly efficient laser. First of all, woe befall the army. Suddenly bullets are irrelevant. But more importantly, you take that gargantuan laser and you fire it at that nuclear pellet, and lo and behold, it begins to fuse, and it actually gets so hot thanks to that nuclear fusion that it is outputting 1.1 watts of energy. You have fired a watt of energy at a chunk of nuclear fuel, and it has produced 1.1 watts of energy. Congratulations, you have a really fucking hot marble. But you only have one of them. Now you need to do that again to another marble to make that into a really fucking hot marble. And do this about 100,000 times.
Now,
a minute.
Yeah, now the understanding of that fusion reactor facility in Canada is that they have managed to make fusion reactors that can do that. The question is scaling that up and getting it cheap and getting it to a point where it can be used commercially to some degree, that it's actually useful. They're not even close to that. They need to tweak it.
Why 3 of 12 here is a smart man. Because he understands the concept of scales of economics.
It's gonna have to be big, folks. It's gonna have to be real big. I can't really show much of the video, or else we might get, YouTube might get mad. But I put it in the chat so that people can look at it. And this was posted some years ago now. This facility, they've been working at it for a while. They suspect that somewhere between 15 to 30 years, they are going to crack the ideal possible parameters for their reactor. And then they're just going to scale it up from that point onwards.
Problem is, though, is that in order to use the nuclear fusion pellet method, you need to basically have a system that can be efficiently reloaded without losing any of that energy, be aggressively radiated out at all times.
Right, because if the scale is too large, then it's going to start to become impractical. After all, you can only operate vehicles so large by a single or even a team of human beings before things get clunky. It can't be the size.
In the channel, Ratking in the YouTube chat there has asked where my channel is. I don't have one. If you want to find more of me, you have to go on other people's streams. Like, for example, Yiz the Eunuch.
Yeah, that's why we did this on my channel, and I'm sort of just letting him waffle as much as he likes while I get these things nailed down, which I seem to have to a large degree. I had to do some Googling while he was talking.
I'm having a tremendous amount of fun, by the way.
Also, it's past 3 now, so did you need to go?
I have to be gone by the end of the hour.
Then I suggest that we wrap things up here pretty soon.
Maybe a good call. But before we go, let me just waffle about one more subject. That being the initial subject that you wanted me to waffle on. Planet X. So, there are a variety of objects known to the scientific community and to the hatred of everybody else as dwarf planets. These are objects that are large enough to have gravitationally coalesced themselves into a sphere or sphere-like object, but have not gained enough masses to be able to have established themselves in a circular orbit around our sun, nor have they been able to effectively clear all of the orbital debris from their orbital path.
Yeah,
what that
I see
means
it. I
is
see a
that
considerable possibility of space noids inhabiting these.
So, the dwarf planets exist as a variety of objects. See here at the top of the second paragraph, there is Pluto, Eris, Haumea, Makemake, Gogua. The names get a little bit more obscure the further. The smaller they get, the more obscure they get, because they started running out of Greek and Hellenic gods to draw from, you see. But, yeah. Most of them have one thing in common. That being that they're really fucking far away. The only two that aren't really far away are Pluto and Ceres. Pluto is also really fucking far away, just not quite as really fucking far away as the other ones. Whereas Ceres, that is actually the closest of all of the dwarf planets, being located in the asteroid belt. It's the dwarf planet next door. It's cute. I like Ceres. Unfortunately, Ceres is tiny. So, the interesting thing, the reason why I'm talking about dwarf planets in relation to Planet X is because there is a really weird thing that all of those dwarf planets do. And that is, they all have different orbits that all appear to have their most distant extent of their orbit all on roughly the same side of the solar system. If you imagine a big circle, in fact, let's make things really... Bree, could you do me a favor
Sure.
and quickly do a Google image search of the Google logo.
Okay, Google search
Google
the
Chrome, the Google Chrome logo specifically. Now we'll wait for the YouTube stream to catch up so that I can actually take a good look at the Google Chrome logo. Or I can just look at it on my end. Okay, so you see the logo consists of 3 parts. There is the sphere in the middle, and there's the green segment, the red segment, the yellow segment. Now, you might suspect that in a given set of orbital mechanics, that all of the various dwarf planets would exist in a roughly even distribution, with each one having an equal amount of chance to exist in either the red segment of this theoretical distribution of solar system, or the yellow segment, or the green segment. They'd be spread out. No, all of them are in the red segment.
Really?
Yep, all of them.
Why the hell is that?
Every dwarf planet that we've ever seen, they've all spun off in the same general direction, and the most furthest aspect of their orbit and the closest part of their orbit, they all are roughly in line with each other.
That implies that they have a similar origin and came about from the same sort of gravimetric slingshot.
No, it implies that there is something called a shepherding object.
Oh.
Now, the thing about orbital mechanics is that they tend to line up one another. In fact, if you could do me a favor and type in dwarf planet orbital paths into Google Images, it should bring up the right image. And for this one, I will have to wait for the stream.
Yeah, I see how they're pretty aligned.
Yeah, it's kind of like the petals on a flower, except half of the petals have gone missing. That image is pretty good because it shows an image of Planet 9. Now you'll notice that Sedna is among those transuranic dwarf planets, and Sedna is the one that we know the most about because it's the largest. However, all of those dwarf planets, they do all get ejected off in roughly the same direction. And because of the way orbital resonances and the laws of orbital mechanics works, typically speaking, when you have multiple objects orbiting roughly the same orbital plane, they tend to want to balance themselves out. A good example of this would be the way Trojan asteroids work. At least I believe that's. I'm referring specifically to asteroids that share the same orbital plane as a large planet. Let's say, for example, on Jupiter, you have the various Lagrange points. They consist of asteroids that get kind of stuck into an orbit that either trails behind Jupiter but on the same orbital path, or they will be slightly in front of Jupiter on the same orbital path. There will also be a collection of asteroids that are somewhere between the Sun and Jupiter, again, locked in place for the most part, and there'll be another one that are slightly further out, again, in a direct line between this Lagrange point and Jupiter and the Sun. They all have their own special names. It's all very... that's just one aspect of orbital mechanics. They tend to... It means that objects tend to influence each other's gravitational pulls in very unexpected and mathematically boring ways. But the thing about orbital mechanics and the dwarf planets is that the fact that they all share the same general orbital path, that being they are unbelievably one-sided, lopsided, say, is that these lopsided orbits are so phenomenally unlikely to have actually occurred. Like, I think somebody actually ran the maths on it once and figured out that the chances of all of these dwarf planets just so happening to all orbit with their most distant aspect of orbit all being in roughly the same direction with none of them on the other direction, there's like a 0.01% chance of that happening randomly.
Which means there has to
It's
be
absurd.
a
Which
gravitational
means,
source that's shepherding them.
yeah. So either we exist in a solar system that is a fucking fluke of a solar system,
Which some would love
or
to just jump on because they have
oh
this,
yeah,
human soul-centric idea that we're just special and we're the center of the universe and whatnot. Even though
but
that's
no.
highly
As a
unlikely.
matter of fact, as a matter of fact, our solar system is actually rather boring grand scale of. The only interesting thing that we've so far been able to observe about our solar system that all the others is the fact that we're here. But all that aside, the number one source of evidence as to the fact that Planet 9 exists is the simple fact that the dwarf planets exist. And the dwarf planets exist all sharing the same general direction of orbital mechanics, meaning chances are there is another really big source of gravity that also has an equally elliptical orbit but goes in the other direction so that everything balances out on average. And the thing about Planet 9 is that in order for it to actually exist and follow these kinds of orbital mechanics is that it would have to have a rather large mass to be able to affect all of these other much smaller objects, but at such a unbelievable distance. Which is why they estimate that planet would have roughly 10 times the mass of the Earth.
Jeez. Yeah, that's what I learned about it when I was a kid. It's what made me so interested in the concept. If we ever, one, it asks why haven't we been able to spot it via like methods like microlensing, and two, if we do, it's going to be fucking massive. So it could be.
Well, here's an interesting thing about micro.
Yeah.
In a rather interesting case of reversed expectations, microlensing is one of those methodologies that they use to find objects that work better the further away the object is.
That's not far enough away.
It's way too close.
Damn.
If you think about it, the way microlensing works is that it takes an object that is unbelievably far away, like another galaxy, and as that light travels towards us, that light that other galaxy is emitting is traveling in all directions in a sphere. But eventually, when that light has traveled such an unbelievable distance that it has literally traveled from one galaxy to another, those light beams are, for all intents and purposes, parallel to one another. The way microlensing works is you take an object that has a reasonable degree of mass and you look for a light source that has been traveling with parallel laser beams, because you can effectively imagine interstellar sources of light to be emitting lasers at us. That being perfectly parallel traveling streams of photon energy.
Right.
And they get to this well of gravity, and that well of gravity acts a bit like a lens, and it causes all of those streams of light to ever so slightly tweak their trajectory. And what that results in is a ring of that same image that you would otherwise see being ejected in our direction, or projected in our direction, I should say. Now, this is really difficult to do with nearby objects, because the closer the object is, the stronger its source of gravity needs to be in order to be able to, bend a sufficient amount of light for it to be noticeable comparison to the background sources of light that just happen to be streaming in directions. So what that effectively means is that Planet 9 is a bit too close to us to see via gravitational lensing, or detect via gravitational lensing, I would say.
So what's
It's
more
just-
likely to work?
The most likely method that we have of being able to find Planet 9 is unbelievably unlikely to ever find Planet 9.
Ah,
What we'd have to do is we would have to take a very detailed survey of every single object in the general vicinity of that cloud of various micro dwarf planets and figure out what the average opposite orbital mechanic would be.
it's like
So
a
we'd have
puzzle
to-
with a trillion pieces.
Yeah, we'd have to try and it's like a puzzle with a trillion pieces, except we actually have to find all of the pieces first.
I mean, I think with enough of the pieces, you could probably start to approximate it, and then you could send a spacecraft there, and then
You could.
You could.
You could approximate
very
it.
much
But
like
you'd
Eve
never-
Online's scanning.
Okay, so here's the thing. Once you found enough of the dwarf planets and you've calculated to within a absurd degree of accuracy their orbital paths, you'd be able to get an estimate as to the orbital path of the hypothetical Planet 9. And then the only way you'd be able to actually see that Planet 9, because bear in mind it's so unbelievably far away from the sun that it is for all intents and purposes a black hole in terms of its light output, that you would have to wait for a chance event where a telescope happens to be pointing at the right spot, the right time, recording what it's looking at, and then a tiny, and I'm talking like 1 pixel wide line of stars sequentially winks out of existence. That being those stars' light being eclipsed by the volume of Planet 9 itself on its orbital path. The only way to be able to see Planet 9 would not be to directly look at it, but to look for the absence of stars that it is covering over from our perspective.
Mm-hmm.
And-
I could see that working too, but I'm thinking that it might be worth doing something a little bit more direct than trying to observe it from here. Based on the approximations, maybe you could send a probe to the general region, and then basically use some sort of instruments from it, do a general sweep and see if it gets any hits. Like you could simply. Do you think that
so-
like sonar would work? Is there some
Sir?
way that you could use some sort of
Okay, let
method
me-
of detection that
Let me go
would-
through all of those methods with you and explain
Yeah.
why each of them would not be effective. So, first of all, let's go with sonar, the one that you just suggested.
yeah.
Sonar works on sound. Sonar and sound can't travel in space, so that's an
Oh, that's
immediate
true
ruling
because
out of that as
there's
a-
not enough density.
Next potential option would be to look for potential sources of outcoming energy from the object. So that could be the various wavelengths of light.
Yeah.
Now, this is not an energetic object. This is, for all intents and purposes, a ice giant. Ice giants are really bloody cold, and those are the ones that are close enough to the sun that they actually reflect the sun's light.
That's what I was
Planet
thinking.
9? Planet
would
9
ha-
would be so far away from the sun that it wouldn't be able to reflect the sun's light in any meaningful degree. Bear in mind, this object is estimated to orbit for 99% of its orbital period outside of the Oort cloud. Yeah, it's really far away. It's so far
the
away
other
that if you
side
were to
of it.
stand on its surface and look back at the sun, you probably wouldn't be able to tell which of the stars is our sun.
Yeah. Since it's approaching, like what, more than a light year away?
No,
Not
it
quite
is
that.
not more than a light year away. It's a probably on average, Planet 9 is probably somewhere like a light month away,
Okay.
which is very far.
Yeah, it's absurdly far.
None of these diagrams that you're looking at right now are even.
They don't do
vaguely
it justice.
scaled.
Yeah.
Yeah.
Because the scale is much larger than than any of these are implying.
Okay.
And that's why I find these outer objects interesting, is because the scales start to approach ridiculous numbers to the point that getting into them, if any one of these objects are so extremely far away from each other that they basically
Let me
have no direct
let me
contact.
put things into perspective for you. Let me put things into perspective. You're familiar with the size of a soccer ball, right?
Yeah.
Putting this into American terminology. So I just dropped. Anyway, imagine you have a soccer ball, and you take that soccer ball and you put it in the middle of what I'm just going to call a football field. Now, if you were to stand at either end of that football field, and you were to say that that soccer ball was a scale model of the sun, the scale distance of that sun to the Earth would be like, I don't know, 3/4 of the way to the outside of that football field.
Yeah. Yeah, it's just absurd amount of
Lots of open space.
Like, you think the distances between here and a planet like Saturn or Neptune are absurd? They start to really get long once you get past that point.
Continuing my analogy of taking a soccer ball in the middle of a soccer field and then just figuring out where all the various planets are. Earth is about 3/4 of the way out of the center. Where the goals are situated on either end, that'd be like where Mars is. Go a fair bit outside of the actual field itself, like, go down the road by a few city blocks, and you might be somewhere in the realm of maybe Saturn. Go to the outskirts of the town, where it starts getting into the, where the wealthy people live. Around there, it's kind of where Neptune is.
Here we go. Here's a much more useful
Go to
scale.
Go to the next town over. That's beginning to get into the realm of like where Planet 9 the like is. Yeah, there we go. That's a pretty decent scale.
I
see
did
how
look up
see how Neptune. See how
Yeah.
Neptune is roughly 3 times further away from the sun than Saturn is, and
Yeah.
then look at how far away Eris is.
Yeah,
in
approximately
comparison.
30 AU. So
Yeah.
many of these outer objects, there's very few that exceed the 90s.
Yep.
Like, that's
Now,
the sort of scale that we're talking about.
if you-
Like 3 times as far away, some of them. Like Eris being less than
If you was-
70.
Yeah, if you were to take a look at the distance, if you were to measure the distance of a hypothetical Planet 9, it would be somewhere in the realm of like 120 AU.
Jesus.
Because of its high mass. It is way out there. It is so far out there.
That would really push the limits. Like, because I've looked these up at some point. There's virtually nothing that far out. So it could be the farthest out object, period.
Yeah, it could very well be. Like, look, how far away is the Oort cloud in AU?
Here we go.
Quickly see if you can find that. Just type in Oort, OORT.
Let me open up a new tab for that.
In fact, I'll look myself. How far is the Oort cloud?
Ranging from 2,000 to 200,000 AU.
Yeah.
Like at the point the outer edge of it is like 3.2 light years. It
Yeah,
gives
it's
you an idea of what really interstellar space is. It's actually a bunch
Yep.
of spheres of outer objects that
yeah, it's outside the heliopause.
yeah.
The thing about Planet Nine, it's thought that the outer reaches of Planet Nine's orbit causes it to skim the Oort cloud, and that when it gets to the outer reaches of its orbit, it disrupts the Oort cloud with its gravitational effects, causing some of the Oort cloud's comets and debris to fall into the inner solar system, which is what causes things like the late heavy bombardment and other other anomalously high degrees of asteroid strikes across the solar system that, according to our best estimates, seem to weirdly come in waves for no apparent.
Yeah, I mean, this scale is very useful for that. Does that imply that Planet X's orbit is highly elliptical?
Ridiculously so, yes.
Like, to the point that it's basically a line in space.
Planet Nine's orbit would likely follow a trajectory that would have its inner orbit be somewhere around the same as the likes of the transuranic objects,
Yeah.
with its most outer orbit going well outside of the heliopause and touching the Oort.
God, it must take forever to get back and forth.
Oh, it does. Millions of years. That's not an exaggeration. Millions of years for a single orbit.
Yeah. I mean, it also means that, after you exit the Oort... this actually makes me realize something. If the Oort cloud goes that far out, 10% of the way to... Well, more than that. I mean, Alpha Centauri is like, what? 4 something light years? If the Oort cloud goes out most of the way out to the next star system, does that mean Oort clouds tend to rub up on each other?
That's logarithmic.
I know, but
that's a logarithmic scale. The Oort cloud is the Oort cloud doesn't interact with other stars until they get within about 1 light year.
Right, but isn't it likely that other star systems also have their own Oort clouds?
Oh yeah, highly likely.
That implies that you wouldn't even really, and although you would need warp speed to get to anywhere in a reasonable period of time, that you could have supply networks that directly connect star systems.
Not really.
Well, I mean, if
you've got to understand, the distance of each individual object inside of the Oort cloud can likely be measured in significant fractions of an AU.
Oh, I know that. I know that. Implying that you already have...
Calling that a network is like saying that that you and me are on a network. Based on nothing but proximity.
Well, another implication that you already have, like, say, faster than light travel. The idea that you could go from the edge of one system and then go to the edge of another system through their Oort clouds and gather supplies from some sort of well-known station that's on a specific object. Entirely possible to pick it up and to know where it is, based on either a combination of mathematics or radio broadcasting, or... I mean, there'd be some way to identify these way stations, but it means they're not necessarily... It means that supplying between systems doesn't necessarily have to be such a long trip. You could literally... The
thing about discussing faster than light travel is that light speed is less of another notch along the speedometer and more of an outright barrier that once you are able to surpass it to any degree, you may as well be able to surpass it to any degree, please.
Yeah.
Once you get to the like Star Trek tends to operate on the logic of each warp speed being a linear scale.
It depends on the series. They tweaked it. After the original series and original movies, they switched to a logarithmic scale, so that
But my point is that by thinking within the paradigm of various different levels of warp speed, you are largely, how do I put this? You're deluding yourself into believing that there will be a linear rate of increase of maximum speed. Once you get to the point where the logic of brute forcing yourself past the light speed barrier
But
is
you're not.
feasible and doable, once you get to that point, you can basically just keep on going along that line of logic until you're quite comfortably at the point where you could theoretically traverse the entire universe instantly.
They explore that in some cases, but that still it's still implied that it requires a specific amount of energy to extend yourself to higher and higher speeds, because of the way that they go about getting around the maximum speed of light. The idea is that you're not even operating with Newtonian mechanics. You're not actually moving. The idea is that you exist in this sort of subspace bubble, and you're moving space, not the ship.
I'm aware of the Alcubierre drive. So, unfortunately, we have gone approximately 37 minutes over what I was expecting us to be going for.
Right.
Which means that we have now been streaming for over 2 hours. Which is a
Yep.
decent stream, I must say.
Yeah.
But, that being said, I have another stream that will be taking place relatively soon.
Okay. Well, then I'm gonna leave it here, and I had a great time, and it was nice to just sit back and listen for once. I really appreciated you taking time and talking to us about this stuff. Hopefully, we can like pick this up maybe in just maybe a Discord chat later, and we can talk about specific things, or we can record it. If you'd like to do another one of these, I'd be entirely comfortable with doing it again, especially since I've looked at these kinks.
3.
Yes.
Let me just say, I've really enjoyed my time here to the extent where if I didn't have other things happening, specifically tonight, I would be more than happy to carry this on for the next 3 or 4 hours.
I suspected that. But
Yeah.
I'm not going to take any more of your time. You get ready. I'm going to let you get ready for the next stream. And I think we should end it here. So, yep, this was good. I agree. Black Taylor's right. I'm glad to see people in chat interacting. This is really nice. In fact, this is the most success I've had so far with streaming. So,
Good.
yeah. I'll see you guys in Cabal. And, well, get out.